In this video, I'm going to start talking about the Bessel functions, which are a different type of special function similar to the Legendre functions I've been talking about. And so I have this written up here because if you remember last video, uh, when I was talking about spherical harmonics, I said that we had this function here that was a solution for our spherical harmonics. But then I only solved for so this is a function of phi. I only solved for these and we were still left with this. So we will see, not in this video, but probably the next video, that this is the radial equation, and this is where the Bessel functions are going to come into play. But like I said, we won't get to how that relates to this in this video. This is just sort of, I guess, sort of a derivation, if you will, of the Bessel functions. But yeah, anyway, next video we will see how how that comes into play in our spherical harmonics. All right, so we have Bessel's equation here, and we know that that we're going to have a solution of the form y equals x to the s times the summation of r equals 0 to infinity of a sub r x to the r, which so this is the form that we are assuming it will be in, and that will allow us to use the Frobenius method. So Frobenius or Benius or something like that. Frobenius method. And I do have a video where I go into how to do the Frobenius method, so I'm not going to go through the whole thing here. But what we will end up with is a set of equations, the first two of which are this s times s minus 1 plus s minus n squared, a naught equals 0, and we will have s times s plus 1 plus s plus s plus 1 minus n squared, and that will be a sub 1 equals 0. And so this one will give us the indicial equation that is s squared minus n squared equals 0, because we're assuming that a naught is not equal to 0. So this gives us the indicial equation, and the two roots of this, so you see it's just some number squared minus some other number squared, and so s is going to equal plus or minus n. And so we're going to get two different solutions, two different independent solutions based on which indicial equation we use. So I'm going to go ahead and use the positive n, and then the procedure would be the same for the negative n, but I'll have a little bit more to say about that later on. So in general, we can get our a sub 2r as minus 1 r times 2 to the 2r times r factorial times n plus 1 times n plus 2, going on and on until we get to n plus r. And then that will be in terms of our a naught. So we can get each Uh, so we could get, a a2 times 0, which would just be a naught, but then a2 times 1 would be a sub 2, and then a sub 4, and so on, using this. So one thing to notice here is that this is going to be, well, if we take this and multiply it by, and I'll talk about this in just a second, what this means. So this gamma function of n plus 1 over the gamma function of n plus 1. So we are multiplying all this, multiply by, so this multiplied by this, and that will equal, so this stuff kind of gets absorbed into the gamma function, which will then be n plus r plus 1 over the gamma function of n plus 1. And so a little, I guess, a little diversion here. So the gamma function, so you'll probably see it written quite often. So my gammas always just look like little hangman things, but will probably look something like this if you just go look it up. So the integral from 0 to infinity of x to the z minus 1 times e to the minus x dx. But what the gamma function is essentially a factorial where n does not have to equal an integer. So if you know what a factorial is, you know that for instance 5 factorial is equal to 5 times 4 times 3 times 2 times 1, and so it's just these integers multiplied by each other. But the gamma function says that n does not have to be an integer, and so that allows us to at least approximate a continuous function where if we had this here and we were just, if we were doing, so we had 1, 2, 3, 4, 5. So 1 factorial would be at 1, 2 factorial would be at 2, so we would plot it just as dots here, and then 3 factorial, so 2, 3, 4, 5, 6 would be at 6, and then obviously 4 factorial is going to be way up here, and 5 factorial somewhere else. And so this is a function where, well, it's not really even a function. Well, I guess it qualifies as a function, but it's not a function the way we often think of. It's not a continuous function, I guess, is what I'm trying to say. But anyway, the gamma function sort of fills in all the gaps, and so that would keep going on. But it's a little weird because there are other functions that could fill in the gaps. In fact, I think if you have the gamma function, if you have the gamma function plus sine of z, or something that looks like this, you get some weird function that looks like this. It's sinusoidal, but it's intercepting these numbers here every time, and so that would be sort of a perfectly valid function that would hit every point on the factorial, and so there you can go down a deep rabbit hole of the gamma function, but for our purposes, well, so a few properties of the gamma function that are interesting to know is that the gamma function of n is actually equal to n minus 1 factorial, which means that n times the gamma function of n is equal to n factorial, because we're just taking this factorial and then multiplying it by n. So that's why you would get that there. And if you actually take the gamma function at 1/2, it is equal to the square root of pi. And in general, the gamma function at any sort of half integer is going to be equal to the square root of pi multiplied by n minus 2 double factorial over 2 to the n minus 1 over 2, where the double factorial is just that it equals product, so product of same parity, where parity means odd and even. And so, for instance, if you had 8 double factorial, that would be 8 times 6 times 4 times 2. Then 1 is just kind of always included because it's defined as the same parity from 1 all the way to n. Or if you had 9 double factorial, that would be 9 times 7 times 7 times 5 times 3 times 1. And so that's what that double factorial is. But anyway, these are just a few quick notes on the gamma function. And so essentially what we're doing is, if we take all this and multiply it by this gamma function, so the gamma function of n plus 1 is going to be equal to n. And so, well, over here, the n plus 1 is r. But anyway, all of this kind of gets absorbed into the numerator gamma function up here, so that it goes from n plus 1 to n plus r plus 1. And so, because it's all of this sort of times the gamma function, which of n plus 1, which, as we know, is just equal to n. But anyway, that's enough about this gamma function. So in general, we can get our coefficients using this. Then when we make that sort of gamma function little substitution there, what we end up with is a sub 2r is equal to minus 1 to the r power times 2 to the 2r power times r factorial times the gamma function of n plus r plus 1. So remember, up here, we when we multiplied all this, we ended up with the n plus r plus 1 gamma function in the numerator. But since this all is in the denominator, this gets flipped upside down relative to that. So we end up with this, and then in the numerator we have a sub naught times the gamma function of n plus 1. And since we have a1 equals a3 equals a5, so that's an a, equals going all the way to a sub 2n plus 1 being equal to 0. So we only have our even functions here, which is what this is telling us. And so we can then say that that our function that we were looking for, so our y from our original differential equation, is equal to the summation from r equals 0 to infinity of a sub naught times minus 1 to the r power times 2 to the 2r times r factorial times the gamma function of n plus r plus 1. And up here we have the gamma function, because I just brought this a naught down in front here, of n plus 1. And then we have our exponents here. So this is 2r plus n. And if we set a sub naught equal to 2n times the gamma function of n plus 1, so 1 over this, then what we end up getting is our y will equal the summation of r equals 0 to infinity of minus 1 to the r power multiplied by, so I'm just switching this a sub naught out for this, so 2n gamma n plus 1, 1 over that, and then just putting this back into here, we have 2 to the 2r r factorial gamma, oops, that's supposed to be a gamma, not an f, gamma of n plus r plus 1 with the gamma of n plus 1 here. Then of course our exponents 2r plus n. So the thing to notice here is that this gamma will cancel with this one. This 2 to the n and this 2 to the 2 to the 2r power will become 2 to the 2r plus n, which is the same exponent that we have there. So we can now, and I will change y, so y equals, and this is the Bessel function, Jn of x equals the summation from r equals 0 to infinity of minus 1 to the r power. And then after canceling out those gamma functions and combining the 2 to the n and 2 to the 2r, what we end up with is r factorial times the gamma function of n plus r plus 1, and 1 over that, and then we have our x over 2 to the 2r plus n. So I just combined these two 2's here and then put that under the x. And so this, as I said, was for s equals plus n in our indicial equation, from above. So if we did this same process to get the r equals minus n, we would get this, which is, I think, sometimes called the Neumann equation. I believe for a different Neumann than the John von Neumann that most people are familiar with, but anyway, we end up with something that looks like this. It's very similar. So r equals 0 to infinity of minus 1 to the r multiplied by r factorial times the gamma function. And so this is where we have a difference. So now we have minus n plus r plus 1. So it's 1 over that. And then we have x over 2. and we have 2r minus n. And so that is for s equals minus n in our original indicial equation. And so these are the two independent, well, they're not always independent, so I guess I should address that. So if n equals an integer, then our solution to the differential equation, which was our y, is equal to either j to the minus n of x, which is equal to minus 1 to the n of j n to the x. And so, for instance, if we said that n was equal to 0, then we would have our j to the minus n of x. I guess I could even put a minus 0 here, is equal to negative 1 to the 0th power, which is just 1. And so our j, it would just be equal to j to the n, which is j0 of x. And so if we had, for instance, n equals 3, say, so j to the minus 3 of x, well, minus 1 to the 3rd power is minus, and so this would be minus j to the 3x. And so if n is a, this is just telling us that if n is a odd integer, then these are equal to, well, they're the same, just with a change of sign, the change of the sign here. If n is not equal to an integer, then we have y, so our solution to the differential equation is equal to some constant multiplied by jn of x plus some constant times j minus n of x. So these two are independent of each other. That's why we can write the solution as a linear combination of the two. If you remember, I guess from my orthogonality video, I mentioned how if they are linearly independent of each other, then we can reduce it down to actually representing it this way, because this is not in terms of this, and the j minus n is not in terms of jn, so these are independent. That is not the case when n is an integer. And so when n is an integer, quite often you will see that they say that the two independent answers are j of n of x and then some y of n of x, which is equal to the cosine of n pi times jn of x minus j minus n of x, and that is all over the sine of n pi. And so I thought about going through and showing that this, so it has to, so we can say that the two conditions that yn of x must satisfy the differential equation, our original differential equation where we started, and two, that yn of x must be independent of of Jn of x. And I thought about going through the proofs of this to show it, but I don't know. Maybe I will in a future video, but it just it doesn't seem like it is that illuminating. So I guess unless you want to look it up for yourself, just take my word for it that this does satisfy these two things. So we can say that these are the two independent uh, answers. These are the two independent answers for our original differential equation. So this kind of looks all confusing and stuff, but uh, I believe in most of what we're going to do, we will be using the Jn of x anyway, and so that is sort of the one that we are most interested in. But anyway, we see up here that we have these two equations. I'll even put a green box around them. These are the two equations here. And so if we actually graph these, I have a picture of that down here that I took from Wikipedia. So if we have the n equals 0, we get this red line here. If n equals 1, we get the green dashed line here, and n equals 2, we get this blue line here. And we see that this is, well, it makes sort of a sinusoidal pattern. But the kind of, I guess, going back to what I started this video on, so change that back to black. So we had our psi of r theta and phi, and we said I said in the previous video on spherical harmonics that the solutions to the theta and phi, so the theta, which is a function of theta, and the uppercase phi, phi, which is a function of phi, that these gave us the spherical harmonics. And the spherical harmonics tells us that if we sort of what values are, so we have a sphere, and it says these tell us on the surface of this sphere sort of what values we have. So you could almost think about it like certain parts of the sphere will be dark while others will be light, and you can actually have this sort of spatial frequency over it, where if you took just a slice off of the surface of the sphere and put it on a one-dimensional thing, it would have something that looked like this on the one-dimensional plane, where it goes from positive to negative. But that is on the surface of the sphere. So what we will have we will see this in more detail in the next video. The radial equation, tells us if this is the center of our sphere, say we are in the center of it here, it tells us what the values are sort of right here, and then moving out and moving out. So at different surfaces. And so you can imagine sort of a nested sphere. I mean, you would imagine that it would be continuous, such that each onion, each layer of the onion would be infinitesimally small as we move in towards the center of the sphere. And that's what the radial equation is telling us. And so this is telling us that at 0, this would be the center of our sphere, and any place on this x-axis would be one of the layers of the onion. And we'll actually see in the next video that there are spherical Bessel functions, and those are going to be the ones we are interested in. So this is all just kind of a preview of what we will see. And so if we, for instance, had our J of 0 and we wanted to look at the sphere this far away from the center of our sphere, or from the origin, I guess you could say, then we would actually take this, I guess, point 2 right here and multiply that by our spherical harmonics and all of that together. So this value multiplied by whatever the value of the spherical harmonic is there would give us what the value of this function is at that particular point. And so that is sort of the physical interpretation of what we are going to be coming to when we combine the spherical harmonics with this with the radial part of our wave function here. But anyway, I think I'm probably starting to ramble on now. I hope you found this video at least somewhat illuminating. I will get into the spherical harmonics in the next video, and we will start getting into, well, I think the next one I'm going to talk about are, well, we'll see. I'm rambling. All right, I will see you in another video.